Okay, today we're at section 1.3. We're going to talk about measurement. How old are you? How tall are you? The answer to these questions are measurements. Measurements are important in both science and everyday life. It'd be difficult to imagine doing science without any measurements. Scientific notation. Why is scientific notation useful? Why is scientific notation useful? Scientists often work with very large or very small numbers. Astronomers estimate there are 200 trillion stars in our galaxy. Scientific notation is a way of expressing a value as a product of a number between 1 and 10 and a power of 10. For example, the speed of light is about 300 million meters per second. In scientific notation, that speed is 3.0 times 10 to the 8th meters per second. The exponent 8 tells you that the decimal point is really 8 places to the right of 3. Now, we'll go over this more math-wise on the board, so don't worry about it. This is just an explanation today. For numbers less than 1 that are written in scientific notation, the exponent is negative. For example, an average snail's pace is 0.00086 meters per second. In scientific notation, that speed is 8.6 times 10 to the negative 4 meters per second. The negative exponent tells you how many decimal places there are to the left of the 8.6. What units do scientists use for their measurements? Scientists use a set of measuring units called SI, or the International System of Units. SI is an abbreviation for Système International des Units. It's French. SI is a revised version of the metric system, originally developed in France in 1791. Scientists around the world use the same system of measurements so that they can readily interpret one another's measurements. By keeping the measurements the same, they can be passed around all over the world, and everybody knows what they are. If you told one of your friends that you had finished an assignment in 5, it could mean 5 minutes or 5 hours. Always express measurements in numbers and units so that their meaning is clear. These students' temperature measurement will include a number and a unit, in this case, degrees Celsius. Base units and derived units. SI is built upon 7 metric units known as base units. In SI, the base unit for length, or the straight line distance between 2 points, is the meter, abbreviated M. The base unit for mass, or the quantity of matter in an object or sample, is the kilogram, abbreviated kg. The 7 metric base units make up the foundation of SI. Length and mass. Temperature is the Kelvin, K. Time is the second, S. The amount of a substance is the mole. You just drop the E for the symbol. The electric current is the ampere, or the amps, capital A. And then luminous intensity, which means how bright a light is candela, and that's abbreviated CD. In this class, length, mass, temperature, time, and moles will be what we talk about. We may touch on amps, but we'll never get to candela. Additional SI units, called derived units, are made from combinations of base units. Volume is the amount of space taken up by an object. Density is the ratio of the object's mass to volume. So density is equal to mass divided by volume. Specific combinations of SI base units yields derived units. So some derived units that could show up. Area. That is just length times width. The unit is the square meter, meters squared. Volume, length times width times height. Cubic meter, meters cubed. Density, kilograms per cubic meter. That's mass divided by volume. Mass is in kilograms, and then volume is in meters cubed. Pressure is the Pascal. We use PA. Energy is the joule, capital J. Frequency is hertz, which is 1 over second, which is Hz. And then the electric charge is a coulomb, which is C. Again, area, volume, density, energy, and maybe frequency. I don't know if we'll get to pressure or not, but we might. But those are things that you're going to see. To derive the SI unit for density, you can divide the base unit for mass by the derived unit for volume. Dividing kilograms by cubic meters yields the SI unit for density, which is kilograms per cubic meter. A bar of gold has more mass per unit volume than a feather, so gold has a greater density than a feather. And we will do something with density later on. Metric prefixes. The metric unit is not always a convenient one to use. A metric prefix indicates how many times a unit should be multiplied or divided by 10. And these are a bunch. You got the giga, which is a billion times, mega, which is a million times, kilo, which is 1,000 times, desa is a tenth, centa is 100th, milli is 1,000th. You got this funny Greek letter mu for micro, which is the millionth, and then nano, which is the billionth. In this class, kilo through milli is what you should be able to know and use, but understand that micro and nano are small and mega and giga are really big. How does the precision of measurements affect the precision of scientific calculations? Precision is a gauge of how exact a measurement is. Significant figures are all the digits that are known in a measurement, plus the last digit that is estimated. The precision of a calculated answer is limited by the least precise measurement used in the calculation. The more precise time can be read from the digital clock than can be read from the analog clock. So this is the analog, this is the digital. The digital clock goes to the nearest second, while this analog clock does not have a second hand, so its only precision is to the nearest minute. So the digital clock is more precise. If the least precise measurement in a calculation has 3 significant figures, then the calculated answer can have at most 3 significant figures. So here we look at volume and mass. When we divide them to get to density, 4 sig figs, 3 sig figs, once we get our answer, we want to round it to 3 significant figures. The density is 7.86 grams per cubic centimeter. This math isn't math that we'll really dig into in this class, but I wanted you to know it exists. Accuracy. Another important quality in a measurement is its accuracy. Accuracy is the closeness of a measurement to the actual value of what is being measured. For example, suppose a digital clock is running 15 minutes slow. Although the clock would remain precise to the nearest second, the time displayed would not be accurate. Measuring temperature. A thermometer is an instrument that measures temperature, or how hot an object is. So this is the parts of a thermometer. The capillary tube. You have the scales. You have Celsius on this side, Fahrenheit on this side. You got a liquid in the middle, and it's a liquid that moves up and down as the temperature changes. The bulb contains extra or the reservoir liquid, and then these lines are the scale. We'll use digital or computer ones, thermometers, just to make it easier, but then would be a simple thermometer, maybe one that you'd see on a wall in a house or outside a building. So how a thermometer works. There's the scale. Liquid rises as it gets hotter, and as the tube gets narrower, it stays in that same temperature range. So the scale's expanded to read, but as it rises, it's used to read the scale. Now the 2 temperature scales that are probably most familiar with are Fahrenheit and Celsius. A degree Celsius is almost twice as large as a degree Fahrenheit. You can convert from one scale to the other by using one of the following formulas, and we'll work with these. Celsius is equal to 5/9 times Fahrenheit minus 32. To find Fahrenheit, you take the inverse, or 9/5 times the degree Celsius, plus 32. Again, Don't worry about these formulas today. A different day we'll talk about doing a temperature scale and doing some measurement there, okay? But this is measuring temperature. The SI base unit for temperature is the Kelvin. A temperature of 0 Kelvin, or 0 K or 0 Kelvin refers to the lowest possible temperature that can be reached. We call that absolute zero. In degrees Celsius, this temperature is negative 273.15 degrees Celsius. To convert between kelvins and degrees Celsius, you use this formula. Celsius plus 273 equals Kelvin. Temperatures can be expressed in degrees Fahrenheit, degrees Celsius, or kelvins. So water boils at 212 Fahrenheit, 100 Celsius, 373 Kelvin. The average temperature of your body is 98.6 Fahrenheit, 37 Celsius, 310 Kelvin. Room temperature, 68 Fahrenheit, 20 Celsius, 293 Kelvin. Water freezes at 32 Fahrenheit, 0 Celsius, 273 Kelvin.